everyone. In our last videos, we talked about the limit laws. In this video, we're going to try and simplify those laws for ourselves by talking about two very special theorems. So the first theorem we want to talk about is about polynomials. It says, if p is a polynomial, then the limit of p of x as x approaches c is equal to p of c. That's very interesting. Did you notice that when we did the limit laws, that the answer actually turned out to be the same as the original question, just all of the x's were changed to c's. If you notice that, great job. If not, that's what this theorem is going to tell us is always going to happen. Very important and very useful for us for finding limits. So, one thing that we typically call this is the plug and chug method. Basically, this says if you have a polynomial and you plug in your value of c, whenever x is approaching is your c, and you get an answer, then that's your limit. Isn't that great? That's going to be an awesome tool for us to use. But better than that is a second theorem. It's about rational functions. The theorem says that if p and q are polynomials, remember we just talked about polynomials in the previous theorem, this takes it further. If we have two polynomials and they are dividing each other, if they build a fraction, p divided by q, and as long as the denominator is not 0, when you plug in c, it says the limit of the quotient, p over q, as x approaches c is simply p of c over q of c. Just plug in your c value that x is approaching, and that's going to be your limit, as long as the denominator does not become 0. Remember, when you have a fraction and the denominator equals 0, then that fraction is undefined. We're going to talk about how to deal with that. So let me look at an example here. Let's see if our theorem applies in this case. So according to the theorem, we have polynomial on top, a polynomial on the bottom. Remember, a polynomial is just terms adding and subtracting, which involve x to a positive whole number power, and maybe some coefficients in front of those terms. So what do? According to the theorem, we simply attempt to plug our c value, which is what x is approaching, so in this case c equals -1. We plug that into the numerator, we plug that into the denominator, and let's see what happens. So up top, if we plug in -1, so -1 to the third minus 2 times -1 squared plus 3. Divide that by -1 squared plus 4. So we simplify, and let's see what we get. So remember, -1 cubed, if you take a negative to an odd power, it's still going to be negative. 1 cubed, well, that's just 1. Minus 2, and then -1 squared. What happens when we square a negative? It's a positive 1. A positive 1, though, it doesn't do anything. It doesn't change the 2, so we're just going to leave the 2. Plus 3. All over, on the bottom, -1 squared, positive 1, plus the 4. So what do we end up with? Let's see, -1, -2, plus 3. That's a 0. Is that a problem? No, the top can be 0. The bottom is where it's important that you do not have 0. So let's make sure. What's the bottom? 1 plus 4 is 5. Do not leave this as your final answer. I see that happen a lot with students. Remember, you have to simplify fractions. 0 divided by 5 is what? 0. Here you go. Okay, so there's your first example of how to apply this rule. You plug in what x is approaching, and as long as it works out that the denominator is non-zero, that is your limit. So the limit for this function as x approaches -1 is 0. Let's try another one. All right, so eliminating common factors from 0 denominators. Wonder what this is talking about. Remember, the theorem we just saw only applies if the denominator of the rational function is not 0. Well, let's see what happens when we evaluate this function at our c. What's c in this case? The 2. All right, what happens when we plug 2 in? So on top we have 2 squared plus 2 minus 6. On the bottom, 2 squared minus 2 times 2. Work it out. I'm going to work top and bottom, but you're going to notice something on the bottom, and that's the important part. But you should work the top too, because it might help you see what's actually happening. So on top we have 2 squared, which is 4, plus 2 minus 6. On the bottom, 2 squared is 4, minus 2 times 2, that's 4. So what do we end up with? 0 divided by 0. What this means to you, first of all, is that this is not the answer. The denominator is 0. That is not allowed when we try and use this technique of plugging in what x is approaching. So first of all, you are not done. When you see 0 over 0, you should start to think about algebra. This is saying that as x approaches 2, we're approaching a 0 in the numerator and the denominator. This might be due to a common factor. So the question is, can we factor this function, simplify it, in such a way that we only affect the function value at 2? So let me show you what I mean. So we're going to take the limit as x approaches 2, and we're going to work this function into a simpler function. So what do I mean? We need to factor. You remember how to factor? If not, you might want to go find some factoring videos to help you review. So on top, we have a trinomial. 3 terms, highest power is x squared, so we're going to factor this into 2 parentheses. Now first you should check for GCF, but I don't see one, so let's see what we get. X squared, break it up, x and x. What 2 numbers multiply to be -6, but add to be the positive 1 in the middle? So a positive 3 and -2 would work. The only option that works. On the bottom, we have an x squared, but we don't have 3 terms. We actually have a common factor. The common factor on the bottom is the x that comes out, which leaves behind an x minus a 2. Why did we factor? Because we're able to see here that on top and bottom, we have a common factor. We have an x minus 2 on the top and on the bottom, which means that you're able to reduce this function. When you reduce this, you are only affecting the x equals 2 value. The rest of the function will still have the same value that it would have anywhere else for any other x's. These 2 are where your function causes the 0 in the numerator and the denominator to happen at x equals 2. So if we consider simply the simplified function, so the limit as x approaches 2 of just the x plus 3 over the x, as we approach the 2, all of those x values, you're still going to get the same function value as the original function. It's just if you plug in the actual 2 that you're going to get a different value. But that's okay. As we approach 2, we're going to be approaching the function value that we're looking for. So what you're going to do is you're going to use the same technique we said before. The limit of this quotient, as x approaches 2, is going to be the same as the function evaluated at 2. If the denominator is not 0. So we simplified our function in such a way that now when we plug in 2, we don't get the original function's answer, but we do find the limit of the original function as x approaches 2. So just plug in the 2 on top, so 2 plus 3, plug in the 2 on the bottom for x, 2, and you end up with 5 over 2, or if you prefer decimals, 2.5. Remember, you only use decimals if it's exact, and we can divide by 2 and get an exact value. So, if you end up with 0 divided by 0 as your limit, try factoring, reducing, and then try plugging it in again and see if you can get an answer. Alright, so there is an example where the theorem originally did not apply, but we were able to use algebra. Algebra is our friend in calculus. And we were able to use algebra to simplify so that we could then apply the theorem and find the limit. Alright, let's try one more. This is actually one that we did back when we did a numerical approximation. We plugged in numbers approaching 2, and we looked to see what the limit was approaching. So today, I want to try and use the theorem. If we plug in 2, what happens? So plug in 2. 2 squared minus 4 over 2 minus 2. 2 squared is 4, so this is 4 minus 4 over 2 minus 2, or 0 over 0. Again, this is not an answer. You cannot leave that. This is simply telling you that you need to go to your friend, Mr. Algebra, and see if he can help you to be able to simplify the function and then proceed to take the limit. Let's try it. So we're going to take our limit as x approaches 2, and we're going to factor the original function. So let me write it first. Notation is always important. You should practice proper notation when you're writing math. So my original limit is equal to the limit of, let's factor. On top you have what's called a difference of squares. That factors into 2 parentheses. This does not have a common factor. It's not a GCF we can take out. So break up the x squared. So x and x, break up the 4, 2 and 2. If you put opposite signs, the middle terms cancel, and you end up with just the x squared and the negative 4. On the bottom, we still had x minus 2. That you cannot simplify. But put parentheses to denote that they are together. They are one factor. Can you simplify? You've done the algebra to factor. Why? Hoping that you can reduce. What can reduce here? X minus 2 reduces, and you end up with the limit as x approaches 2 of x plus 2. Now, what you have done is you have changed your function, but you've only removed the part that caused it to go 0 out the numerator and denominator at x equals 2. Every other x value approaching 2 is still going to be the same as the original function value would have been. But now we're actually able to evaluate at 2. So if we plug in 2, using the theorem of, in this case, the polynomial limits, the limit of a polynomial is simply plugging in your c value into x, and that will give you your limit. This is exactly the limit we got when we did the numerical approximation. So great, you've achieved your goal. We've done it by a numerical approximation, or we've also found the limit by using algebra. Remember, numerical approximation is more time consuming, so it is not good to use that on every problem. However, if you get stuck, go and give that a shot to help you figure out what your goal is. This is much more efficient, and it is a better use of your knowledge that you have. So bring that algebra back, review some factoring. You're going to need it in this chapter especially, but calculus course, you will need a lot of algebra, especially factoring. All right, go study, make sure you understand what's happening here, and then carry on. Good luck.